Hey, thanks everyone for joining us for the second seminar in the Data Science Under the Hood seminar series. So it's a pleasure today that we have Timothy Graham, who's going to give us a talk. Before Tim gives us a talk, let me just give you a bit of an overview about what the Data Science Under the Hood seminar series is all about. So this seminar series is organised by the QUT Centre for Data Science. And the primary aim is to disseminate fundamental and cutting edge data science methods to the Data Science at QUT network. And hopefully this can help to firstly expand the knowledge base of our members, and secondly to potentially foster new collaborations by increasing awareness and highlighting challenges. So I guess that most of you would be participants in the QUT Centre for Data Science. But if you're not currently a participant and you'd like to join, then please let us know, because there's lots of great activities and opportunities that are happening, and it would be great if to have you engage in those opportunities. So just before I pass it over to Tim, let me just read out a brief bio of Tim. So Tim is a senior lecturer in digital media at QUT. His research combines computational methods with social theory to study online networks and platforms, with a particular interest in online bots and trolls, disinformation, and online ratings and rankings devices. He is a CI of an ARC discovery project that utilizes large-scale hyperlink network analysis and web experiments to assess the web presence of 10 countries. Tim develops open source software tools for computational social science, and he is published in some high impact journals in his particular discipline. So now I'm just going to pass it over to Tim, and also keep in mind that if you have any questions along the way, please feel free to type them into the Q&A chat that you should see at the bottom of your Zoom screen. And then Tim, if we have time at the end, then hopefully Tim can address those questions. So let me now just pass it over to Tim.
Thank you, Chris, and thank you to Joyce and everyone at the Centre for Data Science. It's a great pleasure to be here and to participate in the seminar series. I'm just going to quickly share my screen, bring up the slides here. Yeah, so the talk today is around the notion of coordinated inauthentic behaviour on social media, and it's primarily concerned with doing a bit of a deep dive on methods, cutting edge methods that I'm developing in collaboration with other researchers to detect and to analyse this kind of behaviour. So just quickly, I'm located in the Digital Media Research Centre and affiliated with the Centre for Data Science as well. And a lot of the work that I do is similar to research coming out of the DMRC. So please feel free to take a look at that if you're interested. And briefly, before I begin, just a quick shout out to some of my collaborators in the DMRC: Tobias Keller, Dan Angus, Axel Bruns, and Rio Zhu, who are all working with me on this project and taking various roles. So what I'm going to do is divide the talk into kind of 4 sections. The first part, I'll provide a bit of background and context to what coordinated inauthentic behaviour is, and a brief overview of some of the literature that relates to this problem. The second part is very much in line with the seminar series, like under the hood mandate, I guess you could say, where it's very much more about the data science around this method, and more of the kind of formal parts of the algorithm that we've developed and the kind of methodology that's involved. But then in section 3, we kind of take it for a ride, close the hood. I don't want to push this metaphor too far, and take it for a spin. So, you know, I'm kind of excited to look at 3 case studies where we've applied these methods and found significant coordinated inauthentic behavior. And one of the findings is quite, I think it's rather shocking. And this is the first time that we've kind of talked about it, so it's a nice chance to bring that out in the world. And then I'll finish up with a brief conclusion and identify, there's quite a number of areas for future work and challenges that we're facing, and it will involve a whole array of different subfields in computer science and the social sciences. So yeah, hopefully some of what I'm talking about is of interest, and if anyone has any questions, then as Chris said, happy to chat after the presentation. So as a bit of background, I guess many people here will remember that during the Australian bushfire crisis earlier this year, there was a surge of mis and disinformation around that crisis. And one thing in particular was this, that I was, unfortunately at the center of, along with Tobias and other researchers, was a situation where there was a fairly concentrated group of accounts on Twitter who were strongly pushing mis and perhaps disinformation, so maliciously spread misinformation about the causes of the bushfires. And I've got highlighted here an article from The Conversation that I wrote with Tobias, where we kind of charted what we found when we looked at this arson emergency hashtag, and more importantly, how this placed Australia in this unfortunate position where kind of the global information disorder had zoomed in on Australia and had politicized the bushfires and created a lot of confusion and panic and anxiety around it. And then, of course, more recently and now, I mean, I'm giving a Zoom seminar from my house in a sort of lockdown. The coronavirus has brought about its own surge of information disorders, rumors, hoaxes, misinformation, maliciously spread false news and disinformation, particularly around conspiracy theories that are an attempt in many ways to try and understand and make sense of the coronavirus and who might be responsible for it. And some of these conspiracy theories, I mean, they began on the fringes. They begin with kind of your classic, Uncle Arthurs who are sitting in their houses tweeting about this. But over the course of a few months, starting from around mid to late January, there were several conspiracy theories that took off and went viral. In particular, there's three conspiracy theories. One was that the coronavirus was engineered as a bioweapon by China and had been released either accidentally or on purpose from a lab in Wuhan. Another, that 5G was spreading or is spreading the coronavirus. And then Bill Gates has once again found himself at the center of attention for misinformation, disinformation, where he is purported to be involved in the design and financial benefit of the coronavirus. And this has spiraled out of control. I mean, in many ways, the World Health Organization has labeled all of this as an infodemic to align with the pandemic that the virus has caused. And it's gotten to the point where it's not only the Uncle Arthurs of the world, tweeting from their houses. It's not only organizations like QAnon who are organized to promote conspiracy theories. There is sort of large-scale collective action, even like as we see in this article that my colleague Axel Bruns had commented on, going to the streets about this kind of stuff and placarding government about it. So it really is a major problem that we need to, that we're actively looking into at the moment. One of the key issues that comes out of all of this, and this is a question that I'm often asked by the media, and I talk about this with other researchers. Family and friends also want to know, is there any evidence of central orchestration or coordination for these kinds of for this kind of misinformation, for conspiracy theories that are spreading? I guess the question is anyone behind it, and can we tell that? And so if we think about a conspiracy theory like the China bioweapon one, if one account tweets about it, fair enough. That's completely normal behavior. If two retweet about it, within a very short time window together, sure, that can happen by chance, and it will happen quite often, actually. I mean, people are just picking up on this content, and some of them might be retweeting at the same time, or reposting it, or sharing it on Facebook, etc. But the issue that we face is when more and more accounts are starting to amplify and share the same content repeatedly or at high frequency in a short window of time to each other. And it's this kind of behavior that has taken, it has become an object of interest in communication and sociology. And there's two studies in particular by Francisca Keller et al. And by Fabio Giulietto that provide a bit of context for the work that we're doing here and provide the kind of methodological basis that we build on in this work. And this is the notion of political astroturfing. So this kind of cluster of accounts that may at first appear to be acting in isolation to each other or independently from each other, but when we start to map out and do data mining to map the relationships between them, so who is retweeting the same tweet or the same tweets repeatedly and within a really short time window. So for example, within 1 minute of each other, or even within 1 second or at the same time. This approach enables us to not only look at who's pushing this information, so it goes beyond kind of magnification through retweets and through sharing and through volume, but looking at coordination. So groups of accounts that appear to be acting in unison, whether it be retweeting or whether it be posting links on Facebook, as Giulietto have looked at. And then, of course, once we can ascertain that there is evidence of coordination, we can then make the step towards asking, is it inauthentic, or is it some form of political activism or other kind of organic collective activity? And secondly, and this is the notion of attribution that comes out of cybersecurity. Is there any can we attribute it to a source? So, the low-hanging fruit here, the simple example is, of course, Russian interference, the likes of which we've seen since 2016. I mean, well before that. But in the context of social media during the US election and so on, is it possible that these accounts, which are acting in coordination, that may be acting inauthentically, are actually being controlled centrally? So by, for example, the Internet Research Agency in St. Petersburg, or a Kremlin-linked organization, or anyone at all. It could even be for economic purposes. And so building on this, I guess there's other work that is taking up this idea, and I point towards a paper that really kind of began all of this interest in coordination and these methods, looking at the 2014 Japan general election by Schaefer et al. And a paper that I published with colleagues a couple of years ago, where we looked at whether it's possible to derive an understanding of how Russian trolls are coordinating with each other based on the similarity, the point-wise similarity of their content over time. And so we developed a paper where we kind of did a trial run of this, developed a new edit distance algorithm, applied it to a data set of Russian troll activity, and we found that it does a very good job at being able to draw out the natural groupings and clusterings of coordinated activity. So in terms of the methods that we're looking at here, I'm going to provide a bit of a more formal definition and just to clarify some of the terminology and what we are actually doing in terms of these methods. So this is a little dry, but I think it's important to enumerate the different elements of what we're talking about before I proceed further. So in general, we're interested in coordinated messages, not just coordinated retweeting or coordinated link sharing, but developing a method that can generalize to potentially any kind of social media data where we have sufficient information to be able to map out temporally coordinated messaging from accounts on those platforms and potentially between them as well. So ultimately what we are creating is an undirected weighted graph. The nodes in this graph are accounts on given platforms. So let me take the example of retweeting. These accounts are Twitter accounts, and each account has a link or an edge between it, between the other ones, if they have both in this case, both retweeted the same tweet within some time threshold delta. So it could be 1 minute, as Keller et al. have used, or it could be another threshold like 1 second, if you wanted to look at bot-like activity, and I'll talk about this a little more. But essentially what we're doing is looking to construct a network where the vertices are Twitter accounts and the edges represent temporally coordinated messages. And these are weighted edges. So for example, this node v sub I and this node v sub j, they have an edge with a weight of 2. So they've they have both co-retweeted. They've co-retweeted twice, and both times it has been the retweets have been sent within 60 seconds of each other. But down here, v sub I and v sub k have only retweeted once, and there's no connection between v sub j and v sub k. So there's no eligible co-retweets for these. And I mean, these are kind of, it's a little dry, but this is the building blocks of the method that we're looking to develop. And by breaking it down this way, what we're trying to do is to look at how can we generalize this to accept any form of social media data as input, provided that it makes sense to do so. So for a co-retweet network, for example, we only need 4 data points. I mean, this is an absolute minimum. And if we have these data, then we can construct networks like this and discover, coordinated clusters within the network in this way. A big problem that we've encountered, and I think we probably should have known that this was going to happen, was that by the nature of this kind of approach is lends itself to scaling problems. So the number of comparisons between accounts that we have to make given any data set is equivalent to the number of edges in an undirected network. And for small networks, this is not really a problem. So for the kinds of networks that appeared in Keller et al.'s paper, in the work of Giulietto, and even in work that we've been doing previously, small networks, it's not a problem. But once you start to work with reasonably sized social media data, and many data sets will have at least 100,000 or 1 million, maybe even 10 million unique accounts that are in that data set and need to be compared with each other, we run into a quadratic scaling problem. And the example here is shows that if you have 1 million accounts, then when you run the numbers, you've got to make 500 billion comparisons, and it might take a few years to finish, and that's no good. So we have to kind of deal with this scaling problem if we want to make this method work in any reasonable amount of time. And to address this, what we've implemented is a kind of simple divide and conquer algorithm that kind of gets us beyond this quadratic scaling problem. I'm going to run through, again, this is the under the hood section of the presentation. So the approach that we've taken is to take a kind of sliding window approach where we break down the entire data set into smaller chunks in order to only compare accounts with each other, to check if they've co-retweeted within the time threshold, who are eligible. So we're not going to, for example, if we had a data set that spanned 90 minutes and the threshold is 60 seconds, we're not going to compare accounts that only tweeted at the beginning and with accounts that only tweeted at the end. So the intuition of this approach is to take a first stab at trying to make a more scalable co-retweet algorithm, where we sort the data we sort the tweets by the time they're created. We split them up into a number of time slices K, and we can use a threshold like 60 seconds, or we can play around with that. And I'll talk about that in a moment. And then the objective is really to minimize double counting of pairs and only compare eligible pairs of accounts. We use various tricks. Shout out to Rio, our research associate who's been working on this, who's finding all sorts of cool little ways to subset the data and speed things up kind of at each step. But yeah, generally this is the approach we've taken. And then once we've run through all of the time slices, we combine the results and then create a network using the structure that I talked about in the previous slide. And of course, this approach is great as well because it's embarrassingly parallelizable. So you can, we've been really fortunate to have access to the compute infrastructure through QUT with the Ronin infrastructure, and yeah, just using hundreds of CPUs and splitting it over there, really, it churns through the data like really quickly, and it works quite well. It's not optimal, but this is definitely an advance beyond kind of a naive brute force quadratic approach. Just before I jump into the chase and get into the applications of this work, I kind of want to make a few remarks about this algorithm, and mostly this is because this is probably one of the major bottlenecks for this research in just the time complexity issue, where we're routinely wanting to run this on very large data sets. And there's a whole field unto itself, and we have limited kind of capacity to be able to, to write code and to optimize things. So it's really kind of an open call for anyone who's working in this area to, if you have any suggestions or, if you have any tips or anything like that, or looking or keen to collaborate, then I'd love to chat about this later. But I guess the main remarks here are that, kind of fundamentally, at the worst case, time complexity is quadratic. And so, we still have this kind of problem where it's possible that the algorithm won't scale very well. If all of the tweets are kind of bunched up together into the same time periods. But having said that, I guess the remark here is that at the very least, this gets us beyond the current kind of state of the art, at least in terms of the methods that have been implemented for this kind of coordination detection. And we probably end up in a situation that's similar to the fate of similar algorithms like quicksort that usually run, in kind of n log n time. So, it gets us out of like the seriously bad, hot water with time complexity, but we're not quite out of the hot water yet. And this is still an open problem for us. And the other remarks I wanted to make just quickly, and again, this is mostly for anyone who's really interested in the network science kind of aspect. These co-retweet networks that we're developing here in particular, it hasn't really been talked about in the social science literature that much or at all. But one of the issues is that really you have to set a minimum edge weight of 2. So a connection, connections between 2 accounts, they have to have co-retweeted at least twice, because if they've only co-retweeted once, then it's kind of just random chance. They just happened to retweet at the same time once. So removing these is a really useful filter that's worth mentioning. And setting a minimum edge weight of 2 gets rid of 70 to 80% of all edges in the network, but it does very quickly highlight the clusters that are coordinated in some kind of loose way. Empirically, based on the analysis we've done at the moment, if we set a minimum edge weight to 5 or more, this gives us really accurate results for isolating, truly coordinating accounts who are very tightly knit in terms of their co-retweet activity. You might call them kind of strong or accurate kind of coordinated clusters, but the trade-off is that you start to miss out on true positives at the same time. Another remark leading into taking this baby for a spin and giving this method and the algorithm a test drive and showing you the results is that simply by reducing the delta threshold, so that the time window that we accept for considering coordination between two accounts, if we reduce this from 1 minute as it's been used previously, which is quite a liberal kind of limit, down to 1 second. So these are accounts that have co-retweeted the same tweet multiple times in 1 second or less. So basically at the same time, what we end up finding potentially is bot activity or automated actors. And that's a different class of inauthentic, or at least, potentially suspicious behavior that's interesting. And finally, I would again highlight that even though these are computational methods that are highly quantitative in nature, ultimately all of these parameter values and the different filtering techniques that we can use are qualitative decisions. I mean, we have to kind of interpret the domain, the research questions, what kind of data we're using, and the optimal approach is really a question for each case study. And how it plays out, I guess, is an area for future work. So I'm just going to check the time. Yep. So I'm going to run through now, cut to the chase, and look at some preliminary results and approaches to evaluating this method through three case studies. And the first case study that we're looking at here is this is a network, a co-retweet network that I have constructed out of a data set that we've used in a previous publication back in 2018. And what you're looking at here is a data set of 6.5, well, this network is derived from a data set of 6.5 million tweets between over nearly 1.5 million accounts who were tweeting during the first US presidential debate in 2016 in the US. And we've studied this previously. I've got some references if you're interested to follow these up. But I thought it would be useful to re-examine this data set and ask the question, well, was there any kind of evidence of coordinated activity? And in particular, if we reduce this time threshold down for the co-retweet method down to 1 second, so nodes in this network, pairs of nodes in this network have co-retweeted at least twice, minimum edge weight of 2, within 1 second of each other. But in many cases, it's many more times than that. And running this method on the data set gives us quite a lot of coordinated activity. I mean, we find over 25,000 accounts and nearly 90,000 edges or instances of co-retweets amongst them. And this network by itself is interesting because you can see here that there's these clear clusters of accounts that are just heavily co-retweeting the same content over and over and over. But this is the kind of shocking revelation that we've discovered. Really, this is only in the past week or so. And it's when we went back and queried Twitter to look at the account status for each of these accounts. Querying the Twitter API to find out if these accounts were suspended by Twitter, had been deleted. So this includes potentially being removed by Twitter, or whether they're still active as designated by these colors, red, yellow, and blue. And what we find is that there are these just stark big red clusters of accounts that are clearly coordinating together, and it has to be inauthentic because these accounts in many cases are just all have been suspended, or most of them, or in some cases been deleted. So what we can derive from this analysis is, I think, a fairly profound new insight into, something that, this happened nearly 4 years ago, but obviously Twitter was able to eventually detect and suspend and remove the accounts that were coordinating in an inauthentic way. But at that time, they didn't. So, this is data that was live. I mean, this was happening during a really heightened period of communication, 90 minutes. That's 60 minutes of the debate and then 15 minutes either side. And they were kind of running rampant, these accounts. And who knows the effect that this had on political communications and the public debate when you have amplification of content at this scale and with this degree of coordination by accounts that were later suspended. So I think in some ways this is not only an interesting empirical finding, but it's also potentially one way to evaluate these kinds of methods in the absence of ground truth data. To say, well, if Twitter is then removing these accounts or suspending them, then it lends credibility to the validity of these methods. And of course, it raises the question about, well, how much did coordinated inauthentic behavior by these actors affect the outcome of the 2016 presidential election, which we can't answer here. And more recently, we've applied this method to look at Twitter discussions around COVID-19. There's a lot of activity, research activity looking at mis and disinformation and so-called bot activity around the coronavirus. And so I guess this work kind of, enters into that research field. And what we looked at was 10 days of 10 days of activity on Twitter, consisting of 2.6 million tweets that were retweeted over 25 million times. So it's a fairly sizable data set. And we tracked various different hashtags that at that time were kind of general, like organizing hashtags for public discussions around the coronavirus, and an Australian one thrown in there as well. And again, what we wanted to look at here was to focus on coordinated bot activity, or at least coordinated, highly automated activity, by reducing this time threshold down to 1 second and then seeing what emerges. We also made use of a machine learning based bot detection model, TweetBot2, and this was kind of used as a way to triangulate what we were doing and to get a different picture of the activity. And this is a network of highly automated co-retweet activity just around the coronavirus in general. And what we see, and I won't go into too much detail here, is that there's quite a bit of activity during those 10 days of accounts that are clustering together because they're all retweeting the same content over and over with each other. I've just highlighted 10 communities here. If you're more interested, there'll be a report coming out about this. I think the embargo will be released on Monday. So if you're interested, I guess, check out the news on Monday because I have a report that I've been working on with Axel Bruns and the Center for Responsible Technology and Rio Zhu as well. So you might see this next week perhaps. But for now, I guess what we see is that this these methods are useful at detecting clusters of coordinated activity, some of which is inauthentic. And overlaid on the nodes, we've classified each account using the TweetBot2 model. And this model provides a score for each account between 0 and 1, where 0 is very likely or very high probability to be human, and 1 is very high probability to be a bot. So if an account has a score less than 0.2, then we just say it's human. If it has a score greater than 0.8, then bot, and then everything else is kind of indeterminate. And, it's kind of a mixed bag. We do see like cluster 2, for example, is just all bots, and it is a very tight cluster. So, clearly it's doing, it's doing something. Very briefly, here's an example of one of the clusters. Here's a pair of Turkish political bots. They just pump the same content out, exactly the same thing, pretty much exactly the same time, in the same order. And we see lots of this kind of activity in that network. So that's the kind of, behavior that we find. Very briefly, we've also applied this to look at the 5G causes coronavirus conspiracy theory. And we applied it in this case to Facebook data. So again, we're trying to generalize this method. So moving away from Twitter, we went to Facebook using the CrowdTangle API. And this is a co-link network. So these are Facebook pages or groups who have both sent the same link within 60 seconds of each other at least twice. And I guess, without going into any detail, what we find here is plenty of evidence of, at the least, some kind of coordinated behavior. And some of that may or may not be inauthentic, but at the least this provides a starting point for diving deeper and doing that forensic analysis to see kind of what's going on. Particularly for clusters that are rather disjoint from the rest of the network, like this one on the left here. And I know I'm kind of running a little low on time at the moment, so I'm going to move now into the conclusion. So I guess, what are the key takeaways from this work? The main thing, I guess, the main thing is that we see that this kind of coordinated message analysis provides a whole new perspective on the data that we have. So we can apply any number of other methods, different kinds of network typologies, retweet networks, co-mention networks, reply networks, and that. But these methods don't pick up on coordination in the same way that this does, and related work. And what's really interesting to us about this is how it kind of factors into debates at the moment about the usefulness and the validity of machine learning based approaches for bot detection. And I guess in this subfield, and it is a pretty small field, there's a lot of kind of heated debate on Twitter, but it is fairly niche still. There is a bit of there are fairly serious concerns about the accuracy of machine learning based bot detection models. There's two main problems. One is that further evaluation of these models shows that they may not be as accurate as they're purported to be. And the second problem is that they're focused on individual accounts, and so they're not designed to detect patterns of coordinated behavior. So we kind of miss out on being able to detect that using those approaches. It's not to say that machine learning based approaches are flawed in any way. It's just that they don't do they don't detect coordination in a way that we might like. But coordination is an inalienable feature of so-called coordinated inauthentic behavior. It's really difficult to hide this. So, if disinformation operations want to hide it, then they have to stop sending content out in the same order or in the same time or at the same time. And this kind of throws a big spanner in the works, because that's kind of a core part of their approach. So this, this methodology, in a sense, exploits that inalienable feature of that kind of behavior. What we've developed here in terms of the algorithm for co-retweet analysis is a really useful start, and it takes us a long way, but there's still a lot of work to do, and I'll talk about this in a second. But our preliminary evaluation shows that this method is quite useful, and in many cases quite accurate at detecting not only coordinated activity in clusters of accounts and basically giving them to us, but also inauthentic behavior within those coordinated networks in the form of botnets and or troll campaigns. I'll close with, I guess, highlighting 6 key areas for future work, and these will, I mean, this is kind of like a call out to the community to initiate potentially a discussion and to learn about what people are working on, and how we could improve the approach, or what other methods we could and approaches we could take. The first is, the co-retweet algorithm, and our plan to generalize that to any kind of data. I think it's a really useful method. It's taken off in the last couple of years in the social sciences, but given that the fundamentally what we're looking at is these pairwise comparisons between accounts, between data points, it may lend itself well to other sort of newish areas of analysis, like topological data analysis. And so I've kind of taken a bit of a foray, and I'm aware of these approaches and what they might be capable of doing. But there's kind of a bridge that maybe needs to be built between these fields at the moment, and there's some exciting possibilities there. The second area is looking at sampling. So rather than using all of the data, is there any way that we could sample the input in some way, and maybe that would help make it scalable. Thirdly, and I mentioned this already, but generalizing the algorithm, so we can take an arbitrary social media data set, map it to the data points that we're interested in, and then at the end of that get the co-message network that we want. There's a lot of further empirical testing that needs to be done. It will just come down to running these kinds of methods on different case studies and seeing what comes out. But changing the delta, the time threshold, the time window for co-retweeting yields different kinds of insights. For example, bots versus human-like behavior. Network filters as well. Filtering the network in different ways may affect the accuracy of detecting these coordinated clusters. And then finally, applying the method to interesting case studies, maybe historically or even now, looking at COVID-19 with data sets that people have. There's a whole bunch of stuff that we could do, and I guess I've tried to lay out at least what I think are some of the potential avenues. But would certainly welcome any questions or ideas that anyone has for the next 15 minutes or so. And briefly, just before I finish up here, I just wanted to acknowledge the Centre for Responsible Technology and the Australian Research Council, who have who've funded much of this research, and of course the eResearch Office here at QUT that very, very generously, and I mean like very generously, provided a lot of computational resources and assistance to do a lot of this work. Weeks and weeks and weeks of running it at a fairly substantial cost. So many thanks to them. And of course, thank you to Facebook for providing data courtesy of CrowdTangle. Good on you, Facebook. That's a great direction, and to Twitter as well. So thank you for your time, and I look forward to hearing any thoughts that anyone has, or answering any questions. So thank you.
Thanks a lot, Tim. That was a really great presentation, and I really liked how you spoke about some some possible collaborations, because I guess one of the main objectives of this seminar series is to hopefully foster some new collaborations amongst the data science at QUT networks. That was really great. So there's actually been quite a few questions that have been coming in through the chat. So why don't we just sort of go through this sequentially and see how many we get through by 3 o'clock. So we'll start with one by Ashwani. So this question is, any post may be modified a little and then shared on social media. So how do you sort of deal with those cases?
Yeah, thanks, Ashwani. That's a really good, that's a great point, actually. So I guess it comes down to, again, what are you doing when you compare two accounts, pairs of accounts? And I think I mentioned, like early on in the slides, we've done a little bit of exploratory work using edit distance algorithms to look at two, pairs of accounts or multiple, sets of accounts that have written the same, not the same message, but messages that are very similar to each other by some standard measure. So we began with, with a kind of simple edit distance implementation, and then modified it. So I guess what you're saying, any post may be modified a little. So we modified that, that approach to include a bit more of a semantic and temporal based cost for the similarity between posts or messages. So I'm not sure if this completely answers your question, but it comes down to how you switch in and out the comparison function within the algorithm. So we've implemented a co-retweet function. It just looks at each pair and says, did they both retweet the same tweet ID within 60 seconds? But we could easily switch that out and say, is the text that they've both shared in that tweet fall within some similarity threshold? And then we would, and then the output of the function would be based on that. So we could really, you could swap in any function, and I'm hoping that this is where we can start to generalize this framework. So so we can do these kinds of, do that kind of analysis that's more nuanced, I guess, like what you're saying. And the second part, I guess, of your question is we have to consider the keywords as a data point. And you're absolutely right. We could turn attention not just to the actors or the accounts, but also the keywords, and anything else that we can do point-wise comparisons, pairwise comparisons of in the data. So I guess the dream is to be able to eventually throw this into a multi-dimensional space and not constrain it to some very particular subset of information that we can get from social media data, but generalize it to coherently to any number of data points and just see what we can get from that. So I'm not sure if that answers the question, but that's a really good point. Thanks, Ashwani.
Thanks for that, Tim. So our next question is from David. So David's actually a Deputy Director of the Centre for Data Science. So David's got a few questions. So maybe we'll just pick out the first one from his. I'm sure he won't mind if we try to share the questions around a little bit. So the first question from David is about the undirected nature of the network, and have people considered directed graphs?
Thanks. Yeah, thanks, David. In fact, most networks that you see, including the ones that I have used in almost all my previous papers on using social network analysis with social media data, are directed graphs. So introducing undirected graphs does seem like a strange choice. And it may result in information loss, I guess, because we can't ascribe directionality to the propagation of information, as you point out. The use of a weighted undirected graph it's really a heuristic solution, and it comes back to the nature, the sort of interesting nature of co-message networks, or let's just work with like co-retweet networks as the example here. So if we had, they're undirected in the sense that the relationship that we establish between two nodes only designates whether they both have, whether they're coordinating together within some agreed upon threshold. So by virtue of the method itself, it doesn't really lend itself to having directed edges, because let me reframe this. We could potentially derive these co-retweet networks by constructing a bipartite. I know this is kind of under the hood technical, but I guess this is more formally addresses the question. If we had a network which is accounts who've retweeted other accounts, and it was a two-mode network. So there's accounts, and then there's like retweets, and there's an edge if the account has retweeted that tweet. we could derive a co-retweet network by projecting that network, doing a one-mode projection. That would give us two networks. But then the problem is that we lose information about that because we're really interested to filter the edges by time. And so, I mean, I feel like I'm kind of floundering around a little bit with your question here, but this seemed to be the most expedient way to organize the network structure, given that all we want to know is the frequency by which pairs of accounts have been pushing the same identical content over and over. It's maybe an oversimplification, and it may result in unexpected information loss. But I guess we're kind of reproducing the state of the art as such that's currently in the literature, and if there was a way to introduce directionality and to make the method work whilst retaining that in the network, then yeah, maybe that's an area for future work, and I'd love to chat more with you about that.
Thanks, Tim. So I think the next question we have is from Angela. So Angela mentions, what if malicious actors learn how your algorithm works? Can you adapt your solution to handle this situation?
And these are tricky questions for a Friday afternoon. Really good, really good question. I guess we don't have this problem yet because these methods are too new and they haven't been adopted that we know by Twitter or by other platforms. Reverse engineering these algorithms, if they're being used to moderate content and suspend accounts, reverse engineering them would pose a problem for the disinformation campaigns, because in order to hide, or in order to change the way that they behave to throw off the algorithm, or to, in this case, to just not make it work anymore, changing the time from, bumping it up to 3 seconds rather than 1 second or whatever like that, would require quite a lot of work by the campaigners to do that. So it's coordinating together is kind of, they need to coordinate in order to be effective at what they're doing. They need to push content quickly and at volume. And if they start to space it out too much to throw off, this kind of algorithm, then they're being increasingly less effective at getting, the job done. Maybe they're coming in late on a topic because they're stalling the amount of time, the delta between retweeting each other. Or maybe they need to, for bot networks, create more complicated scripts and or use adversarial learning or something like that. So at the very least, it places the onus back on the disinformers to have to do more work to throw off the algorithms. But when when there's, like, machine learning models suffer from a much worse problem, because they operate at the individual account or individual content level. And so that kind of makes it easier to change things up, because there's not this kind of systematic flaw in their method. All they have to do is just, make the content a little different or change their profiles a bit to get around the current models, and then the models are updated and so forth. But here they have to actually coordinate in a different way. So I guess we're hoping that this is hard enough for them to do that that it messes up their detection avoidance strategies.
Excellent. So the next question, we've got about 5 minutes, so probably time for maybe 1 or 2 questions. So let's have a look at the question from Peter. So this one is asking about the future of your algorithm, or possibly related algorithms. Do you see a future where an algorithm within the scope of your algorithms can be used in real time to help workers?
Yeah, so hey PJ, I did my PhD at UQ with Peter. So hello, small world. Thanks for coming along. Again, this is a really great question and deserves it almost like a whole talk by itself by someone much more qualified than I, who works in that area. But I guess one of the problems with this approach is again this scaling issue, and I'm not sure how well it would work. Sorry, there's a phone going in the background. Sorry about that. I'm not even sure whose phone that is. I'm so sorry. Yes. So the issue would be really in doing this in a live would be tricky because we have to. I mean, you have to collect enough data to ascertain that there is coordination kind of taking place, and at the same time, you have to deal with this extraordinary volume of data. And of course, Google and Facebook and other organizations they science the crap out of this, and they have the most amazing database technologies and frameworks and approaches to dealing with this. But I don't know, our humble little algorithm, and the sort of approach that we're using, I think it couldn't be implemented, but I would hope that at the least there's some kind of way that this could be adapted, to at least find the most severe cases of coordinated inauthentic behavior. And I don't know, I mean, personally, I'm really trying to advocate as much as I can, and Axel Bruns and others in that I'm working with as well, to let especially Twitter know about this work and what it finds ahead of the 2020 US presidential election, because that network that I showed earlier, I mean, all of that activity went unnoticed and they got away with it then, but we don't want that to happen again. So, even if there was some kind of basic implementation, or I don't know, some kind of dialogue with the platforms to get them to take this up and to use it in high intensity situations like presidential debates, I mean, it would be great. That doesn't really address, kind of the issue for Uber and platform workers. And I guess, that's a whole other area about inequality and a more critical perspective. But yeah, so sorry, Peter, I can't kind of say much more, but I'd love to chat more with you about it.
All right, maybe we can fit in one more really quick question. I'm not sure if it's going to be quick or not, but at least it's a shorter question, so maybe it might be quicker. So one from Richie, who's also a program director of the centre. Have you tried to use click or star subgraph identification to distinguish the behaviour?
We haven't used those specific methods, but yeah. So hi Richie. It's funny because I remember reading I was on the panel for your PhD student who was who had been working in this area, and in the back of my mind, I keep thinking, wow, it would be really interesting to apply some of those methods and see, how they can work to detect coordinated activity, because they do appear to be, particularly well suited to that. So while we haven't tried to use this kind of approach, I mean, it may unlock the next level or the next evolution of this method. And we're only really starting at a kind of starting point. It's a pretty rudimentary basis. So, yeah, the short answer is we haven't used those approaches yet, but I'd really love to learn more about them and to, chat about any, any ideas that you might have to incorporate that or use different approaches.
Excellent. So we reached 3 o'clock now, so I think we'll have to draw the session to a close. So thanks very much again, Tim, for the really interesting presentation. Yeah, so I think that's it for today. So again, if anyone's interested in joining as a participant of the centre, then please let us know. But otherwise, hope to talk to you again next time for the next talk within the Data Science Under the Hood seminar series.